Alright, so let's talk about some of these other reactions. So last time we talked about a lot of the reactions that specific elements undergo, but most of the time substances that you'll be dealing with will be compounds. Because, as we said, the elements, a lot of them, especially the metals, are not stable in their neutral metallic form because they need to lose electrons to make a noble gas configuration, or their outer electrons are just not held in very tightly. A lot of the non-metals aren't very stable in their neutral form because they need to gain electrons or join with other elements to share electrons. So since most of the time we're not really dealing with elements, not really focusing on how they react too much. Most of the time we're dealing with compounds. And so, as we said last time, when you mix substances together, depending on how stable those substances are and how free they are to move around and have motion and collide and how much temperature there is controlling how strongly they collide, they may collide, whatever those particles are, may collide with enough energy to rearrange the initial way that the electrons are associated around those atoms. Right? So maybe that, maybe there will be a collision and some bonds break. And then maybe another collision will occur and some bonds will form. There's lots of different ways electrons can be arranged. An atom could have electrons picked off of it. It could grab electrons off a different atom. It could break a covalent bond and form a new covalent bond. It could break a covalent bond by having both electrons leave with one atom, and that would give you, one atom has that pair all to itself and the other atom doesn't have any. It could break electrons more evenly, so one electron goes with one atom, the other electron goes with the other atom, and that would create temporarily, usually for only a little while, these things called free radicals, where instead of having a pair of electrons, it has one single electron in an orbital that doesn't have a partner. So lots of different ways that electrons can be arranged. Lots of different changes that can occur for the electron arrangement. But if there is a change in the electron arrangement, that's what a chemical reaction is. Right? So as we've been talking about, if you have a change in the electron arrangement around the atoms, you'll have the reactants, you'll have an arrow, you'll have the products. Right? The products will be different somehow in the arrangement of the electrons around them. And we can do calculations around that. We did a lot of those already this morning. So we want to look at some more specifics related to the types of reactions and some of the most common ones. So one of those is an acid-base reaction. There's a couple different definitions for what acids are and what bases are. But there's really one pattern of electron rearrangement that really kind of defines an acid-base reaction. So let's take a look at what that is. So Arrhenius defined early on what an acid is and what a base is based on some of their characteristics. So Arrhenius' definition for an acid is that it produces H+. So an acid is something that has a hydrogen bonded to some element or group of elements. In order to get an H+, that hydrogen has to leave the electrons behind. So when an acid reacts in a reaction, what it does is the electrons, instead of being shared evenly, they get pulled toward the rest of the molecule away from the hydrogen. And the hydrogen is alone. The hydrogen doesn't have a noble gas configuration anymore. So that's really unstable. Right? That's why we avoid exposing our skin to acids. Because if an acid produces an H+ that needs a pair of electrons, it will start to share electrons with pretty much anything. You've got molecules all over your skin that have oxygens and elements, nitrogens that have lone pairs of electrons. So if any of those molecules have a lone pair of electrons, and that hydrogen needs those electrons to make its noble gas configuration, and it comes in here and collides, it will start sharing those electrons. And that can change the structure of molecules. It can make molecules unstable and cause them to start breaking up. So that's how you get a burn from an acid. What makes it an acid, though, is that originally, like HCl, the bond between the HCl, the H and the Cl, is not very stable. The chlorine is better at pulling the electrons than the hydrogen is. So if this molecule is just sitting there, it's not going to act as an acid. Or if it's moving very, very slowly, it's not going to act as an acid. It still needs a collision, just like the other chemical reactions we talked about. It still needs to collide with something. It's stuck together, and the electrons in the bond kind of act like glue holding the atoms together. If that collides with something, the glue can't hold. And so since the chlorine attracts the electrons more than the hydrogen, it can break, and the hydrogen can be without those electrons. So that's basically how an acid behaves. A base, by the Arrhenius definition, is something that produces an OH minus in water. And that's true, but probably the best way to think about a base, the easiest way to think about it, is rather than memorizing the Arrhenius definition, is to look at the Bronsted definition. So by the Bronsted definition, which is probably more frequently used, because it allows us to get a more clearer picture of what's happening with the electron rearrangement in the reaction, the acid plays the same role. In the Bronsted definition, the acid is a proton donor, or an H+ donor. Right? The word proton is often used to just talk about an H+, because a hydrogen has a mass of 1. Most hydrogen atoms have a mass of 1. They only have 1 proton. And so if their electrons are pulled away from them, they don't have any electrons. They're just one single proton. That's what's in the nucleus of a hydrogen with no electrons around it. It's just a proton. So as we said, HCl is a good example of an acid, because if a collision occurs and the chlorine grabs the electrons away from the H, you get an H+. And a Cl-. So the H+ is produced. An acid is something that produces H+ or donates an H+, gives away an H+. So a base, by the Arrhenius definition, produces an OH-. But since acids and bases react together, it's more intuitive to think of the base as being the partner of the acid. The acid is giving away an H+, the base is accepting the H+. So really what an acid-base reaction comes down to is a transfer of an H+ from one substance to another. And because H+ is so unstable, normally an acid will not react unless it's in the presence of a base. Because to act as an acid, this HCl has to break this bond, produce an unstable H+. It doesn't have a noble gas configuration, and it has to hang out, wait for some element to come around with a lone pair of electrons that can share with the H+. But that's really unstable, and this bond is very difficult to break in that situation. So instead of thinking about it happening step by step, where the acid first gives up an H+, and then the base finds the H+, what normally is the better way to think about it is to think about, if I have HCl reacting, it really needs an acid with it. I'm sorry, it is an acid. It really needs a base to be put in with it. Whatever the base is will accept the H+ from the HCl. But usually it will do that at the same time that the acid is pulling the electrons away from the H+. So one way to think about this is to think about this bond between the HCl. It starts to break, and these electrons are moving toward the Cl. So the hydrogen is starting to become more positively charged because it's losing its electrons. They're moving to the Cl, and the Cl is starting to become negative. If there's a a base nearby, it's much easier for the chlorine to pull the electrons away from the hydrogen, because what a base has in order to be a proton or H plus acceptor is a pair of electrons that it can use to start sharing with the hydrogen as the old bond to the hydrogen leaves. So the hydrogen is never totally without electrons. It doesn't have to really have its noble gas configuration broken for any period of time longer than just a tiny bit of a split second. So during this collision, it's really a collision between both of these molecules, the HCl molecule and whatever the base molecule is. Could be NH3 or some other base. The base has a pair of electrons. So this molecule and this molecule are moving around, they collide, and the base uses its pair of electrons to start forming a new bond with the hydrogen at the same time that the old bond is breaking. Just in that one split instant during the collision, the old bond breaks, the new bond forms. All at the same time. That way, for just 1 second, it's actually much less than a second, but for that one tiny instant in time, the hydrogen doesn't have a noble gas configuration. As soon as that instant is over, now the hydrogen is bonded to the base. And the chlorine is now without the hydrogen. So overall, what happened in that process where the electrons were rearranged? Well, my substance that was an acid donated an H plus that it used to have attached to it to the base, and now the base has the H plus. Right? So the Bronsted definition is nice because it allows us to characterize actually what's happening in the reaction. The acid gives away an H plus, the base uses a pair of electrons to pick up that H plus and start sharing electrons with the H plus. So here's another kind of visual way to show that. Here I have ammonia, which has a lone pair of electrons. So really that's a minimum requirement for something to act as a base. It's got to have a pair of electrons it can share. Usually on a base you'll either have a full negative, or in this case because of the electronegativity difference between hydrogen and nitrogen, the nitrogen is attracting electrons from the 3 hydrogen atoms, pulling those electrons, creating a partial negative. So you can have a full negative or a partial negative on a base. That helps it to attract the H plus. In this case, my water, which normally we don't think of an acid or a base, we normally think of it as being neutral. But really what neutral means, neutral doesn't mean it's not an acid or a base. Neutral means it's either an acid or a base. Neutral means it can go either way. It just depends on what you put in with it. So water is neutral because if I put an acid in water, water will act like a base. If I put a base in water, water will act like an acid. It can act like a base or an acid, just depends on what I put in with it. So if I want to test a substance, if I have a substance, I want to know, is this substance an acid or is it a base? If I put it in water and see whether the substance pulls an H plus off of water and acts as a base to accept an H plus from the water, then I know it's a base. If I put it in water and I see that it's putting extra H plus onto the water, then I know that substance is an acid. So in this case, when I put the ammonia into water, the ammonia acts as a base to an extent. It uses its lone pair of electrons to start sharing a bond with one of these hydrogens from the water. And since oxygen is much more electronegative than hydrogen, it's pulling electrons away from these hydrogen. That creates a partial positive on the hydrogen, partial negative on the oxygen. Right? We already know how to predict polarity of bonds, and we use electronegativity differences to see the electrons in bond shifting. So what this means here is that if I have a partial negative and a partial positive, they attract. And so when I put ammonia in water, I'm already, and these molecules are moving around, the negative end of one and the positive end of the other are already attracted. So that helps line them up during the collision. If they're approaching one another, they're not just going to collide in some random orientation, depending on, just randomness. One molecule has a positive on one end, the other molecule has a negative on one end. So even if they don't start approaching one another during the collision lined up properly, the charges will help them attract, and during the collision they'll line up during that approach, and the pair of electrons on the base will slam into that hydrogen, and the force of that collision can break this bond that was here, and these electrons will stay on the oxygen. So the oxygen will have now 3 lone pairs instead of 2, taking on a negative charge. And now if the nitrogen during that collision starts to share its electrons with the hydrogen, it will form a new bond. And now it will have 4 hydrogens attached instead of 3. And now it will carry a form of positive charge. All acid-base reactions are reversible. So that was one of the common misconceptions that I tried to address early in the semester. Sometimes students get the sense that physical processes are reversible, but chemical processes are not. That's totally not true. Most chemical processes are perfectly reversible. Here's a great example of one. And any acid-base reaction is at least somewhat reversible, because if these two collide with enough energy, when I form the new bond between the nitrogen and the hydrogen, this is my base, it's accepting the H+, this is my acid, it's donating an H+. But then when I form the products of any acid-base reaction, I always have the possibility of it going back, because now I have a negative here and a positive on the hydrogen. So if the oxygen uses its lone pair to collide, if they happen to smack into one another, to collide with that hydrogen of the NH4, then I'll just do the proton transfer back. I'll transfer the H+ back to the oxygen, and I make the reactants. So in reversible reactions, this double arrow is an indication that the reaction will go both ways. And since I've got this sample with lots of billions and billions of molecules, and are just moving around and colliding, at any given instant in time, I've got a lot of molecules reacting from the left to the right, and I've got a lot of molecules reacting from the right to the left. So everything is happening all at the same time. Here's another example. Here's an example where the water is forced to act like a base instead of an acid, right? In the last case, we saw the water donating this H+. That means the water is acting as an acid. In this example, the water is acting as a base. Not because water is any more basic than it is acidic, but because I happen to put an acid in water, it forces the water to act like a base. So the acid here is HF. HF is an acid that can donate an H+ because the fluorine is very electronegative. It pulls these electrons away, creates a big partial charge. So we can start to see as well early in the semester when we were predicting bond polarities and looking at where the partial charges on the molecule are. Not only does that help us to predict the physical properties of liquids and solids and based on their intermolecular attractions, it also helps us to predict the outcome of chemical changes. When molecules collide, if one molecule has a positive somewhere on it, another molecule has a negative somewhere on it, those charges will line up during that collision, and it helps us to see what bonds might be most likely to break and how they would break. So in HF, the bond between the fluorine and the hydrogen is very likely to break because the fluorine is pulling the electrons away, pulling both of them away from the hydrogen. So that makes this hydrogen here a partial positive and susceptible to undergoing an acid-base reaction. So since water has 2 lone pairs on the oxygen, and that oxygen has a partial negative, when these collide, the partial negative on this electron pair maybe collides with that partial positive on the hydrogen, and it starts to form a new bond there as the old bond between the hydrogen and the fluorine is breaking. So those 2 molecules collide with enough force, we break the old bonds, and then we instantly start to form new bonds. So the oxygen now has 3 hydrogens attached to it, and the fluorine has 0. The fluorine keeps the electron, right? So the acid always keeps the electrons. It only gives away the H without the electrons. And that's because the base uses a lone pair to replace the old electrons with a new pair to share with that hydrogen. So in this case, the water is acting as a base because I have an acid. So can we think of any other structures for molecules that could act as both an acid and a base? What are the requirements for some that act as an acid? What types of structural features on the molecule allow it to act as an acid or a base? what do we need if we're trying to imagine another molecule that could act as an acid or a base? What? Yeah, so if it's going to be an acid, the minimum requirement is it needs to have at least one hydrogen somewhere. If your molecule doesn't have any hydrogen, it can't be an acid. It can't be a Bronsted acid. It has to be able to donate a hydrogen, so it has to have a hydrogen to donate. What else do we need for the molecule to be an acid? Yeah, we need either a highly electronegative atom that's ripping electrons away from the hydrogen, or at least an atom that can stabilize those electrons once it gives the H plus away. So whatever this element is, it's got to at least be more electronegative than hydrogen to attract the electrons away from the hydrogen. And once the hydrogen is given away, it has to be able to stabilize those electrons. That's really the key feature. If I have an atom that can grab a lone pair of electrons and it doesn't make it too unstable, then that atom should be able to pull those electrons off of hydrogen. And it will be facilitated by a collision, right? So even if the hydrogen and whatever the element are sharing electrons fairly effectively, it's relatively stable. If it bangs into something really hard and this atom's more electronegative, the electrons will go to it. And if it can be stable that way, it will stay that way for the most part. And that will make that substance a good acid. So usually that means that you need a fairly electronegative atom. So what about for a base? What are the features we need for a base? It's got to have some element involved in it that has a lone pair. And that element either needs a negative or at least a partial negative. That will attract it to the H plus and allow it to form a new bond with the H plus. So there are lots of molecules that could act as both an acid or a base, right? Water is one of them. Water has this feature here, the OH. That makes this hydrogen acidic. But it also has the oxygen with a lone pair and a partial negative. That part of the molecule is basic. So any molecule that has an OH attached to it, you could have a carbon and an OH. You could have a carbon with a double bond O and an OH. Any feature, any atom with a lone pair of electrons could potentially act as a base. And any time I have a hydrogen attached to an oxygen or a nitrogen or one of my halogens or any of the more electronegative elements, even maybe a sulfur, then I have the possibility that that hydrogen could be acidic. So generally, though, what I don't see are hydrogens attached to carbon as being acidic. Right? The reason for that, so if I've got a carbon here bonded to a hydrogen, or other elements that are low in electronegativity like boron, silicon, phosphorus, those elements, when they're sharing electrons with carbon, don't pull the electrons very strongly from the hydrogen. So when I have carbon sharing electrons with hydrogen, this hydrogen is really not susceptible to being picked up by a base and sharing electrons with a base, because this bond is already pretty strong. And if it were lost, if this hydrogen were picked up by the base, the electrons would have to remain on the carbon, and as a small, low electronegativity atom, it can't really stabilize those electrons effectively. And so carbon hydrogen, boron hydrogen, phosphorus hydrogen, silicon hydrogen, those bonds are not going to be acidic. But you can see sulfur, chlorine, bromine, iodine, fluorine, oxygen, nitrogen, any of those elements sharing electrons with a hydrogen could potentially act as an acid and leave that hydrogen without any electrons. So that's a lot of variety of molecules. And so there's tons of different acids and bases that exist in nature, which is why it's one of the first reactions that we talk about specifically in general chemistry. All right, so what we already said was that these processes are reversible. And that means at some point we will form what's called an equilibrium. So if I have an acid, generically A, it's bonded to a hydrogen, it's attracting the electrons, it has the possibility to donate the hydrogen, and I've got a base with a pair of electrons. That pair of electrons is going to be shared with the hydrogen. If they collide, the base will start to share its electrons with the hydrogen. The old bond will break, and so the acid will keep those electrons it was sharing the hydrogen to itself, and the base will start to share its pair with the hydrogen instead. Right, so that's the forward reaction. But as we said, the reverse reaction can also happen because now, if this is my acid, this is what we call the conjugate acid, or this is the conjugate of the acid. That's the conjugate of my acid. It's the same molecule, but it's after the acid donates its H+ and it doesn't have it anymore. So now instead of an H+ there, it has a pair of electrons that it used to be sharing. And if it was once sharing with an H+, it at least has some capability of again sharing with the H+. So if this acid conjugate, which is now acting as a base, because now it has a pair of electrons it could potentially share, starts to share its electrons with the H+, and these electrons get pulled back, then I go back to what I originally started with. And so I will create an equilibrium eventually where I have some quantity of substances on this side existing, this acid and this base, and some quantity of this, which has the potential to act as an acid now. This is the conjugate acid. This is the conjugate acid of my original base. Because now it has an H+ attached to it, which it could possibly donate. So now it's more acidic. So if I have my acid and the base come together, it could pick up the H+, produce the product. But then I have the reverse reaction. The new conjugate base could pick up the H+ and go back to its original form. So this will be happening, constantly happening. So it's often also called dynamic equilibrium because once the reaction gets to an equilibrium or a balanced state, I won't see the quantities of reactants and products changing anymore, but that doesn't mean the reaction has stopped. It means that if I look at some time period, like 5 minutes, in 5 minutes, a number of these will collide to produce the product, and the same number of these will collide to produce the reactant. So these reactants are constantly producing more products, but the products are constantly producing more reactants at the same rate. So I don't have any net change in the amount of reactants or products once the equilibrium is reached. So every acid-base reaction will produce an equilibrium to some degree. Some acid-base reactions, though, are considered strong, and others are considered weak. And the distinction between strong and weak is really artificial. It's not a real distinction. But we use it in textbooks anyway, so we have to understand what the distinction is. So what this artificial distinction is if this equilibrium, if on one side, if two of these substances on this side or the two substances on the other side are much more stable, then those substances will start to accumulate more when the equilibrium is reached. Right? So I could have an equilibrium where the forward rate and the reverse rate are equal, but I might produce way more products than reactants or vice versa. Right? So if you imagine maybe this conjugate base really stabilizes that pair of electrons really effectively, much more than this base. If the electrons are really stable, then only the strongest collisions, only the most forceful collisions here will cause the reverse reaction to occur. So I could accumulate a huge quantity of these products, and they could be colliding millions of times per second. But if 99.999% of all the collisions are too weak to make the reaction happen, because this is really stable as it is, and it requires a really strong reaction to break up its stability, then the reverse reaction will only happen once in a very great while. So I will start to accumulate large amounts of these products. Okay, so the definition of a strong acid, if I want to know, is my acid strong or weak, what I need to do is to put my acid, with the possibility of having a hydrogen to donate, into water, which can act as an acid or a base. So if I put an acid in water, the water will act like a base. It will use its lone pair, one of its two lone pairs, to pick up this H+. And that will produce an oxygen now that has 3 hydrogens instead of 2 and a positive overall charge. And then the acid, now without the hydrogen, will become really its conjugate base. So if I have a strong acid, that means when I put it in water, that its conjugate base stabilizes these electrons so effectively that even when it collides and does the reverse reaction, very rarely does that collision actually have the force of impact necessary to do the reverse reaction. So when this equilibrium is reached, I accumulate so much product that the amount of reactant remaining is small enough that I can ignore it mathematically. So if I have greater than 99%, and there's no strict cutoff, but roughly 99% products and less than 1% reactants, then mathematically that's about the same as 100%. And so that's what it means to have a strong acid. A strong acid, when I put it in water, I can predict that 100% of this, effectively, will be converted into H3O plus in the conjugate base. And that the amount reacting back is so small that it doesn't really affect any calculations significantly. That's what makes an acid strong. If it's strong, it forces water to react with it nearly 100%. If an acid is weak, then it forces water to react with it significantly less than 100%. So if the acid is weak, it still has a hydrogen it can donate. It still forces the water to use its lone pair to start sharing with that hydrogen and make H3O plus. And then the acid is without the hydrogen, so it's just having a pair of electrons. In this case, the pair of electrons are less stable. So a different molecule, one that's a weak acid, won't be able to stabilize the electrons it holds behind very effectively. And so in that case, even the light collisions, even the weak collisions between these two, when they come and collide together, even the weak ones will allow the acid to use its pair of electrons to grab the hydrogen back from the H3O plus and reproduce water. So in that case, we'll get an equilibrium, and it could be anywhere from maybe the reaction between these two produces only 0.00001% products and 99.9999% reactants. That would be a very weak acid. Or maybe I get roughly a 50-50 mixture, or 20% here and 80% here. Some percentage of reaction, when I get to the equilibrium, when I reach the equilibrium, if I have some significant amount of quantity of substances on both sides, then that's what happens when I have a weak acid and I put it in water. So you want to make sure that you can explain the difference between strong acids and weak acids. So here's our table of strong acids. There are only a few acids that are strong enough to react to nearly 100% with water. And this is, there are a couple maybe that aren't on this table, but these are the only ones that we really need to know, and they're on the formula sheet, so you don't have to memorize them. but you do need to know what it means to be strong. What it means to be strong is that if I put the acid in water, it will react 100%. Not exactly 100%, but almost 100%. Effectively, mathematically, more than 99%. So that will put, usually we just use a single arrow to indicate that the reverse reaction is not significant mathematically. So the H plus from the HCl will go onto the water and make H3O plus. And Cl minus will be left over because the HCl won't have the hydrogen with it anymore. It's just a Cl. Same thing with HBr. If I wanted to react with water to test if it's strong and I see that the reverse reaction is not significant, I would get H3O plus again and Br minus. Same thing for the HI. Same thing for HNO3. Oops. If I put that in water, allow it to react, it reacts nearly or greater than 99%, and I get H3O plus. And in this case, when I lose the H, I'm left over with the NO3 minus. Right? So what's left over after the reaction is exactly what I started with, but with one fewer H. And since the H plus is given away, it's not just losing an H, it's also losing a positive charge. So if the HNO3 was balanced in charge and it lost a positive, that means it's left over with an extra negative. So other strong acids, HClO3, HCl4, maybe just look at this one. If that reacts with water, it forces its hydrogen onto the water. And what's left is a ClO4 minus. So what these all have in common is that the negative charge that's produced is really stable. It's stable because it's on an element that can attract those electrons that create that extra imbalance in charge close to the nucleus, pull them in, make them stable. Maybe there's resonance to help spread that negative charge out and stabilize it that way. Sulfuric acid is interesting because it has two hydrogens that it can donate. So if I put sulfuric acid in water, the first collision between the sulfuric acid and water is a strong acid-base reaction to produce H3O plus and HSO4 minus. So it only loses one hydrogen at a time. It still has one left. The HSO4 minus still has a hydrogen it could donate. However, the HSO4 minus reaction with water is not a strong reaction. It's a weak reaction. So we would use double arrow there to indicate that when that second H plus is donated to the water and I have SO4 2 minus left, this is not quite as stable, which makes sense because if I produce one negative charge that's stabilized with lots of resonance, that could be quite stable. It's only one extra negative imbalance in charge. And so that is not likely to pick up the H plus back and go back. This is going to be nearly 100% forward. But when I give up another H plus and produce a 2 negative charge, that's more imbalance on one molecule. It's going to be less stable. So that will form, but since it's not as stable, if it collides with an H3O plus, it will do the reverse reaction. So some of this will stay in solution. I'll still have some HSO4 minus, and I'll have a little bit of SO4 2 minus formed as well. But in the water, I will have virtually zero H2SO4 because as a strong acid, it reacts nearly 100%. So those are your strong acids. Weak acids, there are thousands and thousands that exist. So there's no table on the formula sheet for all the weak acids. One common type of weak acid is called a carboxylic acid. Carboxylic acids, acetic acid is an example of them. Carboxylic acids have a carbon double bonded to an oxygen and another oxygen bonded to a hydrogen. And then there could be almost anything here. So depending on the identity of this group, it could be one more carbon, like in acetic acid here. It could be 2 carbons, 8 carbons, 100 carbons. It could be a carbon with some nitrogen attached. Since carbon can bond to so many different things in so many ways, there are literally thousands and thousands of possible groups I could put here. But it would still be an acid because of this grouping of atoms here. This is my carboxylic acid grouping. And so what makes that an acid is that if the hydrogen is donated to a base, and I look, so if I lose that hydrogen and I look at what remains, now I have a negative charge, which isn't really that stable. But it's more stable than some negative charges because I have the possibility of resonance. These electrons can swing in here and push these out onto this oxygen. And if I do that, now I have a different resonance contributor with the other oxygen carrying the negative charge. And so we know the way resonance works is that neither of these exists. When resonance occurs, what exists is the resonance hybrid or average of the individual contributors. So since I have one full negative now because I lost an H plus from a balanced charge molecule, that one negative is spread out over this oxygen and this oxygen evenly. So since I have a negative charge, it's a little bit unstable, but really I really only have a negative 1/2 on each oxygen. It's not quite as unstable. So that's what makes it acidic. The fact that when it donates its H plus, it can stabilize the negative charge that results fairly well, means that if I put it in water, it will donate the H plus to some extent. And so if I put acetic acid or vinegar in water, I will get some H3O plus. That's what makes it acidic. But it's not a strong acid because the conjugate base of the acid with the negative charge, although it's stabilized by resonance, it's not really very stable. This reaction is a great way to gauge how acidic something is and how stable something is with the negative charge. To what degree is this resonance stabilizing the negative charge? Well, it's stabilizing it enough that if I put vinegar in water, I make a pretty acidic solution. Compared to putting ethanol in water, which has a negative ion oxygen that's not stabilized by resonance, if I put ethanol in water, it's not really acidic. It's basically neutral. So without that resonance to stabilize the negative, if this resonance couldn't occur, this hydrogen wouldn't be given away at all to any significant amount. It wouldn't even really be an acid. So what makes it an acid is the fact that it can donate the H plus to a water and still be somewhat stable. And that stability means that if these collide, only the stronger collisions will allow the reverse reaction to happen. And that means I will accumulate some of these products in the reaction and I will still have some of my reactants left over as well. And that's an equilibrium because I'm not doing 100% complete reaction. I still have something left over on each side of the equilibrium. That's what makes it weak. Bases react with water. Instead of donating an H plus to water, they accept an H plus from water. Right? So the definition of strong and weak is applied here in the same way. If I have a strong base and I put it in water, it will react nearly 100%. So NH2 negative is a less stable negative charge than an OH negative. Right? Because oxygen with the negative, it has one proton more than nitrogen does. So it can pull electrons in, bring them close to the nucleus, make them more stable. And so if I have an unstable negative, that will be very likely to grab an H plus from the water and become more stable. As a consequence, the water loses its H plus, it's acting as an acid, and it produces a negative charge. But which side of this equilibrium will be favored is going to depend on which side is more stable. And since the oxygen can stabilize the negative better than the nitrogen, significantly better, when I put this molecule in water, it will react nearly 100%. That makes it a strong base. So I don't expect you to predict whether something's going to be strong or weak generally if I just give you a substance. But we do have a list of strong acids on the formula sheet. So if I give you an acid and it's not on that list, you can assume that it's weak. most of the strong bases already have an OH minus present. Right? So if we think about this strong base, it produces an OH minus because it grabs an H plus off of the water. So other strong bases may already have an OH minus intact. And so then just dissolving that substance produces OH minus. So these are also considered strong bases because as a solid, when I dissolve it in water, if the positive and negative ions completely separate, I produce 100% OH minus. Right, so any base that when I put it in water produces 100% OH minus, nearly 100% by either breaking up and it already has the OH minus present, or by pulling a hydrogen off the water and making an OH minus, that's considered a strong base. So when you're looking at a list of strong bases, look for a metal and an OH minus because that already has the OH minus intact. And I won't expect you to know these offhand, but anything that has a negative that's less stable than an OH minus will also be strong because it will want to pick an H plus up to balance out that negative if it's really unstable. We talked about monoprotic acids, HCl. So HCl only has one hydrogen that can donate. What about acetic acid? Is acetic acid monoprotic? Does acetic acid only have one hydrogen it can donate? Yeah, this is only one hydrogen. Acetic acid is monoprotic. There are other hydrogens here, but these hydrogens are not acidic. Why? Right, because they're attached to a carbon, and if these hydrogens were pulled away and the electrons had to stay behind on the carbon, carbon is not good at stabilizing a negative charge. So that bond is much stronger, and there aren't going to be any collisions at room temperature that can break that bond. And even if there are some really strong collisions that do break this bond, and the hydrogen leaves and the carbon stays with those electrons, that's really unstable. It's going to find that hydrogen and bring it back in to stabilize those electrons. So at any moment in time, I'm not going to have a significant amount of carbon with negative charge. It's really not going to be forming to any significant degree. But this hydrogen is acidic because the oxygen can stabilize the negative charge because it's more electronegative and through the resonance that we mentioned. So that is a monoprotic hydrogen, monoprotic acid as well. So if you only see one hydrogen on the molecule that could be pulled off and leave behind a stable pair of electrons, then that would be monoprotic. Let's take a look at this simulation here. It gives you a nice visual depiction of what's happening when you put in acid and water. So here I have pure water. So this magnifying glass just allowed me to see what molecules are present. So in pure water, maybe I want to look and show the solvent. So their water molecules are in gray. And then in blue I have OH minus, and in red I have H3O plus. So what is happening here? In pure water, shouldn't all of the molecules be H2O? Why do I have H3O plus and OH minus if it's pure water? Right. So water is neutral. But that doesn't mean, as we said, it doesn't mean that it's not acidic or basic. It means it's both acidic and basic. So what this means is, if my water molecules are bouncing around and moving, unfortunately this doesn't have motion to it, but if you imagine the gray molecules bouncing around and moving, at any temperature, there's some moving slow, there's some moving fast. The fastest ones, if they smack into each other, and they definitely will because it's just chock full of water forming hydrogen bonds, if they smack into one another with enough energy, one water molecule will act as a base and grab the hydrogen from the other water molecule, which is acting as an acid. And so the one will pick up that hydrogen and become H3O plus, and the other one will have the hydrogen picked off and become OH minus. But that's unstable. So if they find each other again, they'll go back to the water. So That's an equilibrium. I have the forward reaction happening and the reverse. If I allow it to happen, I will produce some constant concentration of these. Only a few, but I will get some of them at a constant concentration. The concentration I will get is 1 times 10 to the minus 7th mole of H3O plus. Dang it, H3O plus per liter. That's a really low concentration. So that's the concentration of H3O plus and the concentration of OH minus in water. So what if instead of having water, I add a strong acid? What's going to happen? Well, I'm going to get a lot more H3O plus. And I'm not going to have really any significant amount of OH minus. I will have some, but probably not very measurable amount. So what's happening here is if I have an acid in water, now even the weak collision, because the acid can be stable without that hydrogen, even the weak collision, that acid will donate an H plus to the water, and so I'll get a lot of H3O plus. So I have a lot of H3O plus all over. A lot more than I would normally have. If my strong acid has a concentration of 1 mole of HA per liter, what will the concentration of H3O plus be? How many moles of H3O plus per liter of water will I have? Once the reaction occurs, it should be 1, right? Because if it's a strong acid and I only have effectively one way, that means that all of this acid should be reacting. And for every mole that I have, I should produce a mole of H3O plus. This should be a 1-to-1 mole ratio, assuming it's a monoprotic acid. So I can predict the concentration of H3O plus quickly from a strong acid because I know all of it will react and be converted effectively into H3O plus. If I'm dealing with a weak acid, what do I expect to see? I expect to see much less H3O plus. Right? So here what I have, not only, well, let me get rid of the water for a second. So the water molecules here, maybe just clutter things up a little bit. But if I ignore the water for a moment, I still have a lot of unreacted acid. But some of it is donating H plus to the water and producing H3O plus. But since the H3O plus and the A minus are not that stable, if they collide, then I get the reverse reaction. So the key is, with a weaker substance, I have more of the reverse reaction, some of the forward reaction, some of the reverse reaction. So if I had 1 mole per liter, 1 mole of a weak acid per liter, and I put that in water, can I predict the number of moles of H3O plus per liter of water? No, I can't. I need to know more specifics. I would need to know how weak that acid is. Because if it's just pretty strong but not technically strong, then the amount of H3O plus produced here is going to be almost 1. But if it's very weak, then the amount of H3O plus produced is going to be very small. Right? So that just gives you kind of a visual of how acids and bases behave. So we could just quickly look at the other two. A strong base usually already has an OH minus present or will produce one by pulling an H plus off of water. And since that reacts 100%, I get a lot of OH minus in solution. 1 mole of the base will give me 1 mole of OH minus. If I have a weak base, in that case, the weak base, only some of the molecules will pick an H plus off of water. So if I started with a mole of weak base, when equilibrium is reached, I will have less than a mole of OH minus because only some of it will react. Any questions about that? Okay. So if I have a polyprotic acid, and we looked at H2SO4 already, so let's look at a different example. Let's look at H3PO4. It's another acid that's polyprotic. This one actually has 3 hydrogens. If I draw the Lewis structure, there are 3 OHs. And if I look at the possibility for resonance, because the phosphorus can accept more than 8 electrons because it's in the 3rd energy level, if I pick up one of these hydrogens and the electrons stay behind, that negative on the oxygen can be stabilized by possibly moving in to the oxygen, to the phosphorus there, and stabilizing the charge that forms. So resonance helps stabilize that negative. So phosphoric acid, so instead of H2SO4, if we want to look at this one, I've got H3PO4. The first ionization of that involves 1 H plus being donated to a water. So the water will pick up that H plus and make H3O plus, and I'll have H2PO4 minus. Then if the H2PO4 minus reacts again and collides with even a little bit more force and donates another H plus, I make more H3O plus, and then I have HPO4 2 minus. Right, so every time it loses an H plus, it has less positive, so overall it's going to be more negative than it was to begin with. And then this could donate another H plus and produce PO4 3 minus. But every time I create more negative, it's going to be less stable. So the reaction is going to be less product favored. It's going to be more of an equilibrium. It's going to have more reactants present than products. So you just want to be aware that some acids have the ability to donate multiple H pluses. Neutralization reaction, this is really what we've already been talking about. A neutralization reaction is one where an acid and a base react together and cancel each other out. So I really try to emphasize this. So pay close attention to what I'm about to say. The textbook will tell you that a neutralization reaction produces water and a salt. And that is true in some situations, but it is not always true. So when I give you a reaction on the exam, if I tell you it's a neutralization reaction or I tell you it's an acid reacting with a base, do not assume that the products will be a salt and water. What you need to do, if you know something is an acid, treat it as an acid. Allow it to give up an H plus and write what would be left over without that H plus. If you have a base, treat it as a substance with a lone pair that can pick up an H plus. And if that base happens to be OH minus, and only if it happens to be OH minus, when it picks up an H plus, it will produce water. Okay, so when the textbook tells you that an acid-base neutralization produces a salt and water, that is only true when the base is an OH minus. Because water is the only product you get from a situation where a base, it happens to be an OH minus and picks up an H plus, then you get water. If you have any other base in existence, you will not produce water from a neutralization reaction. So just to give a couple examples of reactions that do not produce a salt and water. So what if I reacted HCl with ammonia? The ammonia is a base. So the HCl gives up an H plus. What's left over is a Cl minus. The ammonia accepts that H plus. What I get is NH4 plus. No salt. Well, technically that's a salt, but no water in that example. I could look at a carboxylic acid as my acid reacting with. If I react with OH minus, I'll get a salt and water. If I react with any other base, maybe an NH2 minus. The NH2 minus will pick up 1H plus. It will go from NH2 to NH3. That H plus it picks up will balance out its negative and it will become neutral. And the carboxylic acid will lose an H plus. And now it will have a negative because it no longer has that hydrogen there to keep its charge balanced. So no water produced there. Maybe look at one other example. Maybe I have an S2 minus reacting with HBr. So here I recognize HBr from my list of strong acids on the formula sheet. That donates an H plus, so I'll be left with a Br minus. And when the S2 minus picks up 1H plus, I'll have SH minus. When I had a 2 minus, I had 1H plus, now I only have a 1 minus. So again, I'm not producing a solid water. So make sure, if you know which substance is a base and which substance is an acid, and I could tell you that or I might not. I might expect you to recognize if something has this specific grouping that it's a carboxylic acid. You need to treat it as an acid. Or recognize if something doesn't even have a hydrogen at all, it can't be an acid. It has to act as a base. Or if something happens to be on the list of strong acids on the formula sheet, you recognize it as an acid. If I put something else in with it, it must be a base. So have the acid donate an H plus to the base, and then just draw what you get after that H plus gets transferred over. It's really actually pretty straightforward. Okay. Another example, quick example here. Here we have MgOH2, which is milk of magnesia. If you put this in water, this example demonstrates how the base isn't actually reacting with water, it's just dissolving in water for that reaction. So let's take a look at that one. So MgOH2. So what I recognize here is that I've got a metal that can only make a noble gas configuration if it has a charge and does not share electrons. So that means that the OH, since I have two of them, must have a negative charge. Two negatives to balance out my two positives. So if that's a solid, okay, I'm going to react it with HCl. That's right. For some reason I missed that HCl. I'm going to react that with HCl, which I know is an acid. So in this particular case, what is my base? Is it the magnesium? Is it the OH minus? Yes, the OH minus, right? The magnesium, a base needs a pair of electrons to share. The magnesium doesn't want to have electrons, and it doesn't. It doesn't want to share, it doesn't want to have electrons, it just wants to be with a noble gas configuration all by itself with a +2 charge. So the magnesium is acting as a spectator ion. It's just there to keep the charge balanced. The OH minus is what has the lone pair to share. So when that OH minus uses one of its 3 lone pairs to share with an H plus, I get water. And I will have a Cl minus left. And I will have an Mg2 plus left. But I also want to balance it. How do I balance that reaction? What do I need to do? Well, if I have 2 OHs, both of them can pick up an H plus, so I really need 2 HCl's. So one way to think about balancing this is to recognize that for every base, there must be an acid. For every site to pick up an H plus, there must be an H plus to donate if I want the reaction to be complete. So if I have 2 H pluses and 2 OH minuses, that will make 2 waters and 2 Cl minuses to keep it all balanced. If I want, when I have ions that are produced, I can show them coming together. I can do that if I want to, but I don't have to. Because 2 plus on the magnesium balance out the 2 negatives on the 2 chlorides, and I'll get MgCl2. So that's correct to show that as an MgCl2. Or, since it's in solution in water and the ions probably remain separated, I can show them being produced separately as well. It's the same thing. So this was an example where I do get a salt, MgCl2, and water. But that's only because my base was OH minus.